Folks, so today we are going to be talking about the fundamental theorem of calculus. Yes. I like noises. Okay, or for short, FTC.
Sounds really good. I like that.
It's only fundamental to calculus. All right? But don't forget, guys, it's fundamental, okay? It's actually not that bad. And now we've come full circle.
Theorem.
All right. So, what is the fundamental theorem of calculus? It is going to be the final piece now that allows us to evaluate definite integrals analytically that Ryan was asking about. Okay. So, if a function f is continuous on the closed interval AB and capital F, and again, what does capital F normally, if we're talking about lowercase f and capital F, what does capital F normally denote? What's that? Emma? No? Do you want to record that here to speak into the microphone? No. What does capital F normally denote? The integral, the antiderivative, okay? If little f is like the original function, then capital F is that function's antiderivative. So if a function f is continuous on the closed interval AB and capital F is the antiderivative, right? Unlike derivatives, where if we took the derivative of a function, we call it an f prime, we don't really have something to denote the integral of a function, okay? So we kind of use this capital letter thing. We should
call it the width.
We don't have the authority to do that, unfortunately, though. So capital F is the antiderivative of f on the closed interval AB. Okay? Then. So that's all of our setup there. We have a function, lowercase f, that's continuous on the closed interval AB, and we have a function, capital F, that is the antiderivative of f on that same interval, closed interval AB. Okay? The integral from A to B, so there's our definite integral, right? We have limits of integration here, lower limit A to upper limit B, of f of x dx is equal to, so here's how we're going to evaluate this. It's merely taking your antiderivative of f and plugging in your upper limit minus the antiderivative of f and plugging in your lower limit.
That's it?
That's it. That's how you evaluate a definite integral now. Okay.
Cool.
That's it. So, guidelines.
You did it.
We did it, team. All right, so guidelines for using fundamental theorem of calculus. All right, so a few guidelines here. Step 1, when you want to evaluate that definite integral, step 1, you want to find the antiderivative of f first. Of little f, right? We've already been doing that when we did indefinite integrals. So what I mean by that is we're going to take, if we have a problem from a to b of f of x dx, okay, that means I want you to find that antiderivative of f. And then step 2, once you've found the antiderivative, the generic antiderivative, with the x and the c, the plus c at the end, evaluate the antiderivative function that you just found, right? Evaluate the antiderivative function at the two
A and B.
At the two bounds. Yep, exactly right. Upper and lower limits. Upper / lower bounds.
We just say at A and B.
Yep, at A and B, that's fine. Yep. A and B, that's fine. That's the same thing. And then just subtract the value of the lower bound from the value of the upper bound.
So we have to find C to do this?
Okay, so good question. We'll talk about that here in a second. Okay, so we're going to find the difference of the value at the upper bound and the lower bound. Okay. So, it is not necessary, here to answer that question, this is so funny, it's like you knew what I was going to be. It is not necessary to use a constant of integration. Remember, C is the traditional letter we use for that constant of integration. When you integrate, you get a plus C, right?
Yeah.
In the process. Why do you guys think that is? Okay, but I mean, C is part of it, though. I mean, when you integrate, you come up with that plus C. But what do we then do? Once we integrate and we have that plus C there, we then plug in our A and B, and what do we do once we plug in the A and the B? Subtract. What's going to happen to those C values?
Cancel.
They're going to cancel. They're going to subtract each other. They will cancel each other out, right? So let me just show that to you here.
When we integrate, do we even have to denote the C?
Not a definite integral, no. And so this is where it gets really dangerous, because we're going to now do all these, well, this is where we're going to do all these definite integrals, okay? We're going to do all these definite integrals, and you guys are just going to, like, forget about the C completely. And then later on,
can I do that?
you can, and then later on, I'm going to show you guys an indefinite integral, and you're going to continue doing what you've been doing for definite integrals, and you're going to forget writing those plus C's. And that's going to be, potentially bad, okay? Again, so it's a typical thing. So understand here, the C, the constant of integration still exists here. So when you integrate this thing, you still end up with f of x plus a lowercase c. All right, and I forgot to do something up here, actually. Sorry, let me go back up here real quick. When you find that antiderivative, you can then use this like notation here where we evaluate from A to B. That little like line, that vertical line with A and B like that means evaluate F, capital F, at both A and B. And so then we get capital F of B minus capital F of A, like that. Upper limit minus lower limit. Okay. So anyway, back down to here, right? So then we're going to evaluate this then from A to B. And so you get F of B plus C minus F of A plus E, but it's the quantities.
Oh, I understand.
Say again?
I understand.
Sorry. Yes, thank you, Emma, for saying something. Okay, so again, I'm just showing you here why C is not important, why we don't need to worry about our constant of integration when we're doing a definite integral. When we do a definite integral, we still integrate like normal, and so yes, technically, that antiderivative has a plus C with it. But then when we go to evaluate the limits from A to B, we plug in the B, we do capital F of B plus C, minus the quantity capital F of A plus C, and what's going to happen to those C's? They subtract away, they cancel. It'll be plus C, but then the minus will distribute there, become minus C, so it becomes just capital F of B minus capital F of A. So you can see that the C's go away. Yes. Yeah. All right. Questions on any of that? We're good? All right, let's actually do some. Let's actually do some. Okay. You have a catch-up problem, Ryan. All right, example.
Not operated.
He was trying to catch up. Knock, knock. All right, so evaluate the definite integral using FTC, and then verify by finding the area under the curve. What's the matter?
It's a big old block of ketchup.
Oh, yeah, you need some ketchup. Didn't you say you wanted some ketchup when you came back in?
Oh, yeah.
I only buy bourbon.
That probably takes
That's
so
right.
long to look
It's
around
only the
and
best.
change it to look back there.
I had it for practical, didn't use it, only got it back today.
Burger, man.
Yeah.
I've got some Southwest peanuts.
That's nice.
All right, let's try one here.
That's what was weird as ketchup.
Number 1. For x, integral from 0 to 3 of 4x dx. All right, so we're going to do this the new way we just talked about here. Ooh, I'm supposed to take attendance.
Did you get an email?
Probably.
I wonder how much you say.
You gotta tell us who's here, who's not.
Ryan.
All right, so Tyler, what's the integral of 4x with respect to x?
But it scored up before, but I still don't.
Okay, so, right, integrating 4x, x is to the 1 right now, so we're going to add 1 to the x, 1 becomes x squared. It's 4 divided by that new power, so 4 over 2, which you simplify to 2x squared, exactly right, so I'll go ahead and just write that here. And then evaluating that from 0 to 3 now. All right, so this becomes then 2 times 3 squared minus 2 times 0 squared. Okay, these upper minus lower. Okay, upper limit minus lower limit there. All right. And so let's see here. 3 squared is 9, times 2 is 18, 0 squared is 0, times 2 is 0, so it gives us 18. Yeah, you evaluate this antiderivative at the upper limit minus evaluating it at the lower limit. That's it. That gives you the value of the antiderivative. Now, let's check this. Is this right? So I'm going to go to my graphing calculator here, all right, and show you. All right, we want to find the area under the curve here. So go to the graph. I'm going to do like zoom in a little bit there. Nope, that's not going to be good. 6. Okay. Oop. Zoom 6. Okay. So we want to go from 0 to 3. So from 0 out to 1, 2, 3, there it is. What kind of shape is that? From 0 to 3, what kind of shape is that region? A triangle with a base of 3. So area equals 1/2 base of 3 times the height. What would the height of that triangle be? So 1, 2, 3. The curve here, remember, is 4x. Right, so the curve here is 4x. So at x equals 3, the height would be 3 times 4, 12. Let's see here. 1/2 times 3 times 12. Well, 1/2 of 12 is 6 times 3 is 18, which is what we got there, okay? Right, I understand. The point is I just want to, again, just further make that connection between... Yeah, absolutely. Yep. All right, let's try number 2. All right, integral from -1 to 2 of 2 dx. All right, so Nate, what's the integral of 2 with respect to x? What's the integral of 2 with respect to x? 2x. We're going to evaluate that from -1 to 2. So this is 2 times 2 minus 2 times -1. So 2 times 2 is 4. 2 times -1 is -2. So minus -2 equals 6. All right, now let's check this geometrically. We'll graph 2, and I'll yeah, whatever, that's fine. Okay, so there's 2. Excuse me. And then from -1 to 2, what kind of region is that?
That is going to be a rectangle.
A rectangle. A rectangle with what height?
2.
And a width of 3. Yeah, from -1 to 2 is 1, 2, 3. So 3 times 2 is 6. Okay, so you can see that the areas and the definite integrals match up, right? Okay. Now these are more easy because it's like, oh, clearly, 4x is a triangle. We're able to find that. But this also will now work for curves that we wouldn't be able to use a geometric formula for, or for which we have no geometric formula. All right.
So question.
Question.
On like a tensor quiz,
Yeah.
you will be asked to signal these left Riemann sum or right Riemann sum, and then asked.
You will be specified to approximate the value of the definite integral using, and then whatever sum
and
they
then
want
say,
to use.
like, use the FTC for another question.
I doubt the words FTC will show up in a direction. It'll just say, it'll actually just say evaluate the definite integral. That'll be it.
And then it won't be like a graph or anything.
Yeah, they'll give you the problem. And so actually we're going to see some of those right now. Okay, so let's take a look at some of those. So we're going to do some more. We're going to do 4 here. 4 more, and then I'll cut you guys loose on your own assignment. Okay, so. Yeah, we're doing pretty good here. I know, right? Those catch-up-related distractions.
We're just trying to catch up on our. So I'm going to give you a heads up. You cannot see that.
Sorry.
We're good.
All right. First one here. Let's do the integral from 1 to 2 of x cubed minus 3 with respect to x. Now remember here, I do not need to put these parentheses in, right? We consider all of the stuff between the integral symbol and the dx. That is all grouped kind of together there in the integral symbol, but throwing in the parentheses is not wrong either. You can have them in there, okay, but they're not necessary. Okay. So Ryan, how do we integrate?
Oh boy. All right.
Here.
So you're gonna raise it x to the 4th.
X
but
to the
then
4th.
you have to do 1 over 4 in front of that.
1/4 x to the 4th. Very good.
Minus
Minus 3x, and we're going to evaluate that from 1 to 2.
Yeah.
Okay. Great. So now we'll plug in 2. That's the upper limit. So we're going to do 1/4 2 to the 4th minus 3 times 2. That quantity minus 1/4 1 to the 4th minus 3 times 1. Now, if this were a free response question, what could we do here? Stop. Circle your answer. Okay? If this were a free response question, stop and circle your answer. This is all arithmetic. The AP people will still give you full credit, regardless of that. Now, this is not a free response question, so we're going to actually do the arithmetic here. All right? Do the algebra. Or not algebra even, so arithmetic. So 2 to the 4th is 16 times 1/4 is 4 minus 6. So that's that. Minus, and then let's see, 1 to the 4th is 1 times 1/4 is 1/4 minus 3. Right? 4 minus 6 is negative 2. Ooh, 1/4 minus 3. Well, 3 is the same thing as how many fourths? 12 fourths. So 1/4 take away 12 fourths is negative 11 fourths. Now we'll do plus positive 11 fourths. And now we need to convert negative 2 into fourths. So negative 2 is negative 8 fourths. So negative 8 fourths plus positive 11 fourths yields 3 fourths. There it is. 3 fourths is our final answer. Now, let me show you something crazy. All right, you ready for this? You're not ready for this, but that's okay. All right. Let me. You guys get your calculators out.
He's gonna blast them on.
Get your calculators out.
Should blow my
Get your calculators out. Let me show you something.
You have so many bags.
He's making booby traps. All right. Shh. All right. You can do definite integrals in your calculator, and it will give you the, correct answer kind of thing. So you're going to press the math button, and then you want to go down in the math to FN int. Guess what that stands for?
Oh my gosh, this is so nice with the graphical representation.
Yeah, I know. Yeah, yeah.
Oh.
FN int stands for function integration, I think. It could be finite, and it could be finite integration too. I'm not sure. It might be. I don't know. I always thought it was function, but it could be finite. Okay, now some of your calculators will come up like this.
Yeah.
That's really nice, because then I can just type in 1, 2, and then x to the third minus 3, and then with respect to x, and hit enter, and oh man, isn't that pretty? That is nice. That is real nice. This does not do that, unfortunately, but you can still do the same thing. For this, you have to type in, I believe, the function first. So it's function, comma, lower limit, comma, upper limit, comma, with respect to what variable? Oh, I'm sorry. Yeah, let me see. It's like the orientation of where it is.
Just make it.
There you go. So you see that function, comma, lower limit, comma, upper limit, comma, the variable we are integrating with respect to, and it's syntax, so I didn't do it right. All right, maybe it's 2, maybe it's x, and then it's 1, and it's 2. I forget this. There it is. Sorry. Okay, there's my mistake. Function, variable you're integrating with respect to, and then your lower limit, and then your upper limit. Okay? But there's the answer.
Ketchup.
Put the ketchup away.
Say again? The x is there just to tell it with respect to what variable you're integrating. It's like the dx. So I'll write that up here on the board for you. Guys, you may want to write this on your notes, just so you have that handy, so you can refer to it, okay? So it's, again, math, button, okay? And then it's fn int command, okay? Which I think was, what was that, number 6 or 7? 9. Okay.
You were wrong.
Way off. I was way off. All right, 9, fn int. And then once you have that command, okay, the first blank is the function. The second blank is d, whatever, your difference, you're in respect to d blank, so dx most of the time. Okay, the next blank is lower limit. And the next blank is upper limit. On the AP section, on the calculator section of the test, you may use this. Okay? On the calculator section of the AP test, you may use this. In fact, you will have to use this for some sections.
Did they clear our calculators before the AP test?
I think they do.
I don't know. They may make you do that, yes. I don't remember. Now, alternatively, let me show you something else.
Well, if you get caught using something in
Let me show you an alternative method here, folks. Sometimes these functions get very complicated. You know what I mean? Like it's just very complicated. So one thing you can do, another option. Let's say, for example, that you had it typed into your y1. Let's say you're trying to graph it or something like that. You already had it typed into your y1. If you have it typed into your y1, so let's say I have my function that I'm trying to integrate. It's typed into my y1. You can actually, rather than having to type it all over again down here, you can go to the vars button, yvars, function, and you see the y1. And when you do that, now the calculator is going to use whatever is in y1 and integrate that from 1 to 2 with respect to x, and so then you get it that way too. So this makes it a little bit more neat, okay? This is going to be exceptionally helpful when we go to solve the revolution and like find the area of a region between two curves and stuff like that. It'll be really helpful then. Right now it's not such a big deal, but it is available to you. So again, that was vars, yvars, function, and then y1. No, that works for any of them. It works for, for the TI-83 too. Here, I'll show it to you here real quick. So,
Do you still have to do like the X and...
Yeah, you still got to do the other commands, unfortunately, though, yes. But you can do vars, yvars, function, y1, delete out the other junk, and there it gives you the 0.75 still.
So our only other way to prove the area would be we would have to make an estimation on the graph.
For our purposes, yeah.
Yeah, it's kind of like a big sense.
Or if it was a geometric shape, then you could just find the geometric areas. Okay?
Let's break it out.
So that's pretty powerful stuff, isn't it? All right, let's continue on. We got 3 more we're going to do here.
This stuff is like middle school stuff.
Okay, 3 more we're going to do here. So let's move on. Integral from 1 to 4 of e to the t plus 2 over t dt. Okay, e to the t plus 2 over t dt. All right, now everyone's like, ugh, please don't call on me. Please don't call on me. Please don't call on me. Maya! Your number's up.
Okay, well, e to the t.
It's EC. What's e to the t's integral? E to the t. Okay. 2 over t.
Oh.
What is that? Wait. T.
Use the calculator and just give me the number. No.
Wait, you just do
Okay, so think of it this way. So 2 over t, let me help a little bit here. 2 over t is the same thing as 1 or 2 times 1 over t. So we were really trying to like integrate 1 over t here. What thing, when you take its, yes, natural log, very good. So 2 ln, okay, of the absolute value of t. Okay, good, Maya, very good.
What?
Yep.
Couldn't you just... Oh. Make it 2. Shouldn't you just make it 2 times t... 2 times t to the negative 1?
Absolutely. But the integral of t to the negative 1 is natural log. You don't use the power rule. Because if you integrate t to the negative 1, like our normal power rule would say, okay, if you do that, you're going to get t to the 0, and then... And no.
That makes sense.
Right, we can't do it that way. So it's natural log, right? Because the derivative of natural log of something is 1 over that something. So. Okay, there it is. Very good. And then evaluate from 1 to 4. And so e to the 4th plus 2 natural log of absolute value of 4 minus e to the 1 minus 2 times the natural log of the absolute value of 1. Okay. Are the absolute values necessary in this case? Sorry, made a mistake.
ln of 1.
No, right, because it's ln of positive number 4, ln of positive number 1, so we can really drop those absolute values, okay? But there they are. There's not really a whole lot more we can do here because there's no like terms really combined, so that's kind of like the final answer.
Nope. Isn't ln of 1 0?
Oh, shoot, you're right. Sorry, thank you. ln of 1 is 0. Thank you. Yeah, so this actually equals 0, so we do have some simplification. So I'm going to go ahead and combine that. So it's e to the 4th minus e to the 1 plus 2 natural log of 4. And you could actually bring the 2 up and make it natural log of 16 if you wanted to, but that's debatable whether that's simplified more or not. Okay, as a decimal answer, e to the 4 plus 2 natural log, minus e to the 4 minus e to the 1 plus 2 ln of 4. So you get approximately 54.652. Okay, why don't you guys go ahead and try that on your calculators now. Use your integration on your calculators and see if you can get the same value that we just got using our analytic method there. So go ahead and type that into your calculator. All right, give yourselves that practice. Does anyone not have a calculator handy? You gonna bring your calculator?
You mean Carmen can't do this?
No, Carmen can't do this.
You get one from your brothers.
Oh, actually I did use one of my brothers.
Oh, yeah, you did. I remember that one now, yeah.
Wait, which?
Do you need a calculator rental form?
Because his phone
No,
has
no, I have-
Oh, we're doing this.
Okay, just forgot it.
I just forgot it.
Okay. Yeah, go ahead and type it in.
I know it's in the I just saw this while I was walking out the door, so I grabbed it.
Gotcha.
Wait.
Is it Walker's?
It is a Walker's. But he's not in Waffle. I don't think he's in that. So you just Mr. Richard, you teach Walker?
No, I only had Hunter and Tanner.
Did you have them together?
Hunter and Tanner, yes.
Was it hard? Sorry.
Was it hard? No, I kept them separate, and they're pretty distinct, I would say.
No, were they like? Did they hate
No, they were great. They were great. They would compete a little bit. I could tell every time I'd pass a test, they'd always ask each other which one, what they got on the test or whatever like that. But Tanner looks a lot more like Connor.
Yes.
So,
Walker looks the most different.
in fact, I called Tanner Connor a couple of times. Sorry, but I'm sure your parents do that all the time.
Yeah, well.
Connor's like, yeah, no. Doesn't happen. All right, let's get my stress level.
All right, so there it is. Boom.
Oh, it's a little high.
Matches up.
It's a little high.
I saw Connor's mom once at
I feel
Lowe's.
She just looked tired having all those boys, right?
Alright, let's try
Just
mine.
worn out. All right, let's try another one. Integral from 1 to 4.
It vibrates for that. Can you wanna try?
Okay, we got two more, folks. This is a penultimate one. Here we go. Next to last. Next to last.
What are you trying to do?
No, you put it on the back. Right.
Okay, so that is 3x to the 4th plus 2x squared minus x to the 3 halves all over x squared there. I'll zoom in some more so you can see it better. And just do it on the calculator. No, actually, we can do this one by hand.
No, we can't, but I'm just saying.
It looks like a
But why
quotient
wouldn't
rule
you?
right there.
But why would you, right? Right, so, quotient rule, right?
That's what it looks
No.
like.
No, there's no such thing as a quotient rule
Well,
for
I'm saying it looks
integration.
like what
No, I
you
understand
said,
what you're saying, I
what you-
understand. But I also want to point that out here. So how do we do this then?
Where's that?
Well,
Let's just make the x
you
a
go to
negative.
S and
Okay, so yeah, we could make this x to the 2 in the denominator. We could rewrite that as the integral from 1 to 4 of x to the negative 2 times 3x to the 4th plus 2x squared minus x to the 3 halves. So now we've changed a quotient to a product, but we still don't know how to integrate a product either, do we? Right. We can distribute this x to the negative 2, though, to all three of these terms here.
that sounds horrible.
It's not that bad. When you multiply x's together, when they have the same base, what do you do with your exponents?
You add them.
You add them. Well, so it'll end up being a subtraction, but yeah, we're just going to add. So it'll be x to the 2, and it'll be 2x to the 0, so it's really just 2 then, right? And then x to the 3 halves times x to the negative 2 it will become x to the negative 1 half. 3 halves take away 2 is negative 1 half. All right, so now we can finally integrate this. So I'm going to call on some lucky duck here. Let's see whose number is up. It's Emma. Her number is up. All right. Okay, I'll let you finish writing. Stall tactic.
Equals.
I don't have the bigger calculator.
You've got big eyes.
Yes. So, function, comma, x, comma, lower limit, comma, upper limit, close parentheses, hidden. Okay. Yeah, unfortunately, even though you have, like, it looks the same, it's just, like, one generation back or whatever, and it doesn't have the pretty type. All right, Emma, are you ready? All right, let's do it. 3x squared integrates to be... What's right? X cubed, that's right. Yeah, the divide by the new power, it'll be 3 divided by 3, so it becomes 1. Very good, okay. Integral of just 2 is 2x. Integral of x, or negative x to the 1 half. So we're going to add 1 to negative 1 half, it becomes positive 1 half, and then divide out front by the new power. So the original coefficient was 1, so it'll be 1 divided by 1 half. 1 divided by 1 half is 2. There it is.
Yes, would it be a positive 2?
Yes, because when you add 1 to your exponent here, it becomes a positive 1 half power, and then you're dividing by that new power. So it would be still negative then, because you're dividing by a positive number. Negative divided by a positive.
Yeah,
All right.
1 over n plus 1.
Yep. And so now we evaluate 4 cubed plus 2 times 4 minus 2 times 4 to the 1 half minus the lower limit there, 1 cubed plus 2 times 1 minus 2 times 1 to the 1 half. I made a mistake here. Okay, again, free response, you're done at this point. Once you substituted in this previous step, not sufficient. You must show the substitution. Make sure you use correct parentheses and stuff like that too. All right, let's math this out here though. So 64 plus 8. 4 to the 1 half power? 2, right? It's the square root when you do 1 half. So 2 times 2, so minus 4. Minus 1 cubed is 8. 2 times 1 is 2. 1 to the 1 half is 1 times 2, so minus 2.
This is not going to be 7,360.
All right.
You made a mistake somewhere.
64 plus 8 is 72. Minus 4 is 68. 2 minus 2 is 1, so minus 1, so 67.
That's what I got.
Okay, 67. All right, let's type that into our calculators, folks. So, and I want you to try it too, since you have the funky calculator. All right, type it into your calculator. Make sure you get this right, because again, our calculators are only as good at the math as we are. If we type it into the calculator wrong, the calculator will definitely get it wrong. It's as dumb or as smart as we are. So we need to be smart with the calculator. Use the tool appropriately. So I'm gonna do it here too. I really suggest you all practice just typing this in, making sure you can type it in accurately, because the more complicated it gets, the more likely you're going to make a little, error. So I'm going to dumb my calculator down back to the Stone Age here and do the original thing. So okay, so go ahead and type it in your calculators and make sure you can do this right.
Yeah.
Okay, so would you like me to look at your calculators, or you want to try and figure it out on your own? Oh, well, actually that's okay though, because then you can use Y1, vars, Y bars, and Y1 then, if you put it in the graph.
Yeah, I got 653.8. I got negative 67. Wait, what?
Okay, so you get 3x to the 4th in parentheses, plus 2x squared in parentheses, minus this in parentheses, but then when you divide by x squared, this is the only thing that's being divided by x squared.
Oh.
Hey, I remember
See
that.
that? Make sure you put parentheses around your numerator there.
Bacon.
That was heavy bacon.
Come on, come on.
We have.
I got it. So when in doubt, add more parentheses.
Yeah,
But
well, you can see how complicated it gets, right, with like that amount of parentheses. I mean,
I just put parentheses everywhere, whenever possible.
yeah. I mean, here's so. Let me show you an option for those of you that feel like you might have trouble with this when we have these big rational fractions. Here's an option. Let me show you something. So I can go to my y1, do 3x to the 4th plus 2x squared minus x to the 3 halves. Okay, so I'll put the numerator in y1. I'll put the denominator in y2. Okay, and then when I go to type this in, so just follow along here. I'll put the numerator in y1, the denominator in y2. Function int, vars, y bars, function y1, divided by vars, y bars, function y2. So I'm just doing y1 divided by y2 here, comma x, comma 1, comma 4. And there it is, 67. Variables, I believe. And then y vars, y variables. Okay, so there's an option. If you guys are concerned about that, you can break it up in using your y1, y2. Okay, it's a lot less messy that way. It's very clean. Okay, last one. Here we go. 0 to pi over 4. Uh-oh. We know what those mean. Trigonometry.
I can't believe you.
Okay. So here's our trigonometry integrals, right? So we want to integrate this. Joey, how do we integrate?
Uh-oh.
Secant squared. What is the integral of secant squared? What thing, when you take its derivative, gives you secant squared?
We got that tangent.
Tangent. That's right. All right? And what thing, when you take the derivative of it, gives you cosine?
Cosine. Oh.
The derivative of what gives you cosine?
Negative. No. Sine?
Sine. Yeah, it's sine. Positive sine.
Oh, geez. I don't know what. I thought I was looking at cosine.
Yeah, you're making it more difficult than it was. Yeah. Shh, girls, focus. Okay.
Are you looking at? They put a brick in the sandwich. Wasn't brick.
All right, anyway, focus here. All right, so we want to evaluate here tangent of pi over 4 plus sine of pi over 4, okay, minus sine of pi over 4 plus, tangent of pi over 4 plus sine of pi over 4.
Tangent of 0.
Tangent of 0. See? All right.
Oh my gosh, what's going on?
Okay. So, tangent of pi over 4.
Ooh, that's 1.
1. Sine of pi over 4.
Root 2 over 2.
Root 2 over 2. All right. Tangent of 0.
0.
0. Sine of 0.
0.
0. So the answer is 1 plus root 2 over 2. Yes.
Awesome, Mr. Wood.
Yeah. All right, folks. So there it is. Questions on any of that? We're all good?
Where's the secant button? Oh, yeah.
Secant button, there is no secant button. You have to do 1 over cosine. And that's how your calculator does it.